All right, we're now recording. So if you don't want your image to show, you can turn off your cameras and share the screen and get started. All right, so we're today and Thursday are just kind of getting ahead days. I finished everything I needed to cover for chapter 13. Okay, so again, we're aiming for the test week from today, the 23rd. Here's my new little mini calendar. I got up to some of 14.1. So game plan for today is 14.1 and 14.2. Okay, I actually don't think it'll take that long to finish everything. Okay, and just like the first test, Thursday I'll do 14.3, and then I'll let you reserve maybe after the break if you have any questions about anything from here. This is our shortest chapter, admittedly, 13.1 to 13.4. Okay, so game plan again today. Take notes, but none of this will be covered on the test. Thursday, 14.3 first half, maybe some of second half, and then part of the second half of the class, I'll let you ask questions in pertaining to the test. Okay, and you've already had one test now, so you know how they all work. They're all pretty much the same style. So Tuesday, I'll begin with lecture. I may go ahead with 14.3 or maybe sneak in some of 14.4. Again, I'm trying to gain some days because, of this schedule, but of course I botched this completely. Okay, and even Tuesday the 23rd, I'll let you ask questions, but if that stops, we can start the test earlier. So whenever the question and answer period stops, we'll break for about 10 minutes. I'll send the exam through Canvas announcements, and then you'll take your test, and there we go, just like last time. Okay, so now that you've gone through one test with me, you know how they all work. You need to submit the homework, and just like last time, there's a 70% homework requirement. Some of you are wanting to submit it already. I ask you, please don't submit it until after the class meeting beforehand. So that would be Thursday. So after class Thursday, I will let you start submitting the homework, but please not now. That's too early for me. Okay. And so you have to submit at least 70% of the homework. So I look at your homework very casually, look at the writing on it, look at the writing on the test. If the writing doesn't seem to match, then I get suspicious and stuff like that. Okay. So formally, you have to turn in the homework by half an hour after the test. So let's see, our class ends at 8:25, right? So you have to submit the test by 8:30, take pictures on the cell phone or scan, just like the quizzes. And then I'll give you another half an hour or 9 o'clock. So you have until 9 p.m. next Tuesday to submit the homework. But again, I'll take it earlier if you wish. Okay. So that's what's happening. I'll get started, but I see some things in the chat. So let's see. Yeah, if you came late, then that's fine. Oh yeah, I should admit, yeah, sorry. I do plan to give you a quiz on Thursday, but it will be on chapter 13 stuff. So it'll be kind of like a review of in preparation for the test. So even though I'm lecturing 14.1, 14.2 today, even 14.3, question and answer session, but I'll save time for a quiz Thursday, and it'll be on chapter 13 material. Okay. Submit the homework, not really whenever. So after, if you submit it now, it's too early for all my other classes and so forth. So again, as soon as the day before the test class is over, then you can submit it. So pretend class ends on Thursday at 8:25, then you can submit it starting 8:25 or whenever we happen to finish then. Okay. Let's see, how hard are integration problems? You should know basic integration. I mean, I know in Calc 2, you had some real messy integration by parts and partial fraction, and all that. You should know the basics. Okay, so I guess the fairest thing is whatever I gave you is fair game. Some of them are obviously harder than others, but you should already have under your belt some integration concepts. And of course, you're allowed a cheat sheet, so you can put some basics on integration on your formula sheet if you wish. You're certainly allowed to do that. Okay. All right, so I think we'll go ahead and get started. All right, so I did very little of 14.1 last time. I'll try to do more. Okay, so again, game plan is 14.1 and 14.2 for today. So I'm going off of this. Future reminder, Tuesday, March the 2nd is a flex day. We don't have class that day. So here we go. All right, so back to 14.1, please. You can go ahead and take notes if you wish, but none of this will be on the test next week. So we have a function of multiple variables. Okay, functions of several variables. So we have f of x, y, maybe. It even looks weird because we're used to having f and then inside the parentheses just one number. Now you could have f of 3, 2, function of two numbers. You can have f of x, y, z, 3 numbers, or f of x, y, z, t, and 4 numbers in there, right? All right, so last time I think I just did the introductory problem on weather, I think it was. If I can find a page here. Right, we did a lot with that. Okay, now let's get into a little bit more nitty gritty. Okay, so for some of these, find a domain, find a range, find and sketch the domain of the function. Okay, so I think I'll show you some of these and sketch the graph of some functions. All right. Okay, so problem 21, function of 3 variables. F of x, y, z is radical 4 minus x squared plus radical 9 minus y squared plus radical 1 minus z squared. Okay, so you start off in this case with R3, all of space. Think back to Calc 1, right? In Calc 1, you started off with all real numbers, right? And then your domain got restricted because maybe you were dividing by a negative, dividing by 0 or taking a square root of a negative, or something about a trig function which doesn't allow you to have certain numbers in the domain. Okay, so if you have a function of 2 variables, like 13 last time, you start off with all of R2 and then you throw stuff out because of restrictions. Same thing here, right? We just throw out the line y equals negative x. Okay, so now problem 21, you start off with all of space, R3, okay, where x can go anywhere in and out, y goes anywhere left and right, and z goes up and down, but we might have to throw out stuff. Okay, and you can see right here, 4 minus x squared, that has to be greater than or equal to 0. Okay, so that means x is between -2 and 2 inclusive. Right, you can tell when you plug in -2 or +2, you get 4 minus 4, which is 0. And then anything in between -2 and 2 works, but not outside. So 2.01 isn't going to work, right? Because 2.01 squared is more than 4. So that's no good here. And likewise, 9 minus y squared has to be greater than or equal to 0, which means y squared is less than or equal to 9. So y is between -3 and 3. And 1, that's a 1. 1 minus z squared greater than or equal to 0 means z is between -1 and 1. So I'll write it like this. And I want you to get used to this notation. We say -2, 2 cross like cross product, cross -3, 3, cross -1, 1. You're not doing a cross product or anything. You're just saying this is the extent of x, this is the extent of y, this is the extent of z. Okay, so -2, 2, cross -3, 3, cross -1, 1 is the subset of all of space, all of R3, but x is bounded between -2 and 2, okay, this way, in and out, and y is stuck between -3 and 3, and z is stuck between -1 and 1. So you basically have a box. Okay, so I drew myself a little box here. So that's my feeble attempt at making a box where x goes from -2 to 2, y this way goes from -3 to 3, and z goes up and down 1 unit. And so you have the box, the boundary of the box is included, and anything inside. Okay, so that's the subset of R3 that I have in this particular case. Okay. All right, and let me check the chat. Let's see. So some of you just joined, I got that. About the e to the t and e to the -t, yes, that's the reason why I went over that particular one. Mr. Stewart seems to like that one, so I think I know exactly what you were talking about. Okay. So yeah, that one with the e to the t and e to the -3, now that I showed it to you, that's considered fair game, right? So yeah. Okay, then let's see, 23. Sketch the graph of the function. F of xy equals y. Okay, this is in 3 dimensions now because f of xy is z. Again, z now represents the height. So I want you to give some effort to try to draw the graph of it. So here's what I did. F of xy is y. That's the same as saying z equals y, but x can vary. Okay, so if you look at just the x is irrelevant, just look at the yz plane. And what is the yz plane? That means x equals 0. Well, y equals 0, that I just draw this at a 45-degree angle. Okay, and now what's really supposed to happen is you take this and move it out and move it in. So that's my feeble attempt of trying to show you that plane where that line just comes straight out and goes back in. Okay, but z is stuck at y. It should be like this and just kind of move the line in and out so you end up with a plane. Okay, so that's my attempt to show you that z equals y plane as it is. Again, just think of this, the plane of the floor, maybe, and then just kind of go up and down as the case may be. Okay, 25, draw f of x, which I'm going to call z. Okay, so you have to kind of train your brain that before, whenever you saw, that should be f of x y, sorry. F of x y. So before you said f of x, that's y. Now f of x y is z. Okay, so z is the height. 10 minus 4x minus 5y. Okay, so sketch the graph of that. We've seen that before. It's going to be a plane. So if I put everything on one side, I have 4x plus 5y plus z equals 10. And again, we've recognized that the easiest way to do that is to put down the x, y, and z intercepts and just draw yourself that triangle. Okay, so x-intercept means y and z are 0. 4x equals 10, x is 2.5. So 2.500. Okay, then y-intercept, x and z are 0. So 5y equals 10 means y is 2, so 0, 2, 0. And then on the z-axis, right, z-intercept, x and y are 0, so z is 10. Okay, so 2.500, 1, 2 and a half, 0, 2, 0, 2 to the right, and 10 up. Okay, and then just draw yourself the triangle, and that's good enough. If I tried to extend that plane, it'd be kind of hard to see. It's probably easier to see the plane if you just leave that triangle, right, in space, and just imagine that it keeps going out in all directions, and you can see the plane there. Okay, so just simple graphs like this, I would have you. You notice I avoided anything that's too complicated in the graphs that we had to do, so that's good enough for us right now. Okay. Okay, the next thing I want to talk about is something called level curves. I alluded to it just briefly last time. Here are some level curves, as it were. So rather than actually drawing something in 3D, which is difficult, like that and that and that, these are computer generated. Okay. One thing you can do is just have a 2-dimensional picture. And it's something called a contour map. So rather than putting in 3 dimensions, we can just draw circles like this and say, okay, everywhere right here, the k, the height is 0. Here the height is 1. Here the height is 2. Here the height is 3. And so you can kind of visually see such a picture, right? Here's another such picture. It's 2-dimensional, but you just kind of use your imagination now, right? In 2 dimensions. Now here are the z coordinates. So the height is 100, and now it's 140, and now it's 180, and now it's 220. So you kind of say to yourself, okay, if I'm going this way, I'm walking uphill, right? So rather than coming with a picture like this, you just have a contour map. Okay, sometimes you can do something like this when you're hiking. Maybe when you're hiking, it might be kind of difficult to carry stuff like that, but you can just look at a two-dimensional picture, right? So, okay, if I go this way, I'm going uphill. If I go this way, I'm going downhill, and so on, right? So this is a contour map. Okay, and these are called level curves. So anywhere along here, the height is 0, level curve. Here, the level curve is 2. Everywhere here, the height is 2. Right? So can you picture in your mind, this is the top of the mountain, so to speak, right? The height is 3, it's way up here. And here you're at ground floor, and over here the height is 1 and the height is 2. So you can imagine walking up or you're climbing up, and that's the peak. That's the top of the mountain, so to speak. Okay. So these are level curves. So I'll do some level curve problems for you now. All right, so that would be 45, 47, 67, 69, those kind of problems there. Okay. Okay, 45, draw a contour map of the function showing several level curves. F of x, y equals x squared minus y squared. Okay. Okay, f of x equals x squared minus y squared. Okay, so let me plug in 0. So what do? I just put 0 here and I plug in 1 and -1 and so on. Okay, 0, x squared minus y squared, that's a minus equals 0. Okay, that means y equals plus or minus x. So I draw there y equals plus or minus x, the height is 0. Plug in 1. 1 equals x squared minus y squared. Okay, I recognize that as a hyperbola. Okay, that's going left and right. Okay, so I draw a hyperbola here and here. So this and this are a level curve of 1. The height is 1. Okay, then I plug in -1. -1 equals x squared minus y squared. Well, if you multiply both sides by -1, that's the same as 1 equals y squared minus x squared. Okay, that's a hyperbola that's going up and down. So I'll go up and down like so. So here the level curves are -1. And I also included 2 and -2. I mean, if we go x squared minus y squared equals 2, that just sends it out a little bit more. And y squared minus x squared equals 2, that puts it this way. Okay, so here's a picture of the level curves. So right here and right here at y equals x and y equals -x, the height is 0. Okay, and if I go this way, the height is 1, height is 2, 1, 2. And if I go this way, I'm kind of going down. I'm walking downstairs, -1, -2, -1, -2. So instead of trying to get this three-dimensional picture in your mind of what's going on, you can kind of look at this, right? And if I look at this, I can see, okay, if I'm going here, it's like I'm walking uphill. I can imagine these are steps. Step up 1 here, 2, 3, and so on. And likewise, if I go this way, I'm at ground level, step up 1 and 2, and so on. Okay, but if I go this way or this way, I'm going down. Okay, so if you imagine you're on ground level, right? And if you go that way, the height is now -1. I'm going down 1 unit. I'm going down 2 units. And here, likewise, I'm going down 1 and down 2. Okay, and after a while, your brain might get kind of mixed up trying to think of this because there aren't that many real life situations where, you know, this actually happens where here you're at 0. If you go this way, you're going up. And if you go that way, it's down. And this way, it's down. But they exist. You could actually come up with something like that. Okay. All right, then 47, I was going to show you. F of xy equals radical x plus y. And I tried to just give you the more reasonable ones. 47, f of xy is radical x plus y. Okay. All right, so I'll just plug in some numbers like z equals 0. So this is 0, then y equals negative radical x, right? So y equals negative radical x, that looks like this. So here's z equals 0. Plug in 1, put a 1 here. Again, subtract radical x, y equals negative radical x plus 1. Well, that's 1 unit higher. And then z equals negative 1. Negative 1 is here. Again, subtract radical x. Y equals negative radical x minus 1. Well, that's down here. Okay, so there we go. So here's a picture of this thing. No graph here. Here the height is 0. Here the height is 1. Here the height is negative 1. So rather than trying to draw a three-dimensional object or actually make a 3D graph, just look at this and say, okay, if I go this way, I'm going up. And if I go this way, I'm going down. And yeah, technically it's infinitely far. You keep going infinitely up, 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 or down, 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 as it were. Okay. Okay, what time is it? Oh, we got plenty of time, actually. I'm almost done with section 1. Then I can get started with section 2. It's only 6:35. So we're fine. So 67 and 69, what do they want? Describe the level surfaces of the function. Just give a description. F of x, y, z equals x plus 3y plus 5z, number 67. So if I let k be any number, x plus 3y plus 5z equals 0, equals 1, equals 2. Those are all planes, right? In fact, those are all parallel planes because they all have the same normal vector of 1, 3, 5, right? So you might recall the normal vector is just the coefficients right here, 1, 3, 5. So change the k and you have different planes. Okay, so you can imagine, let me show you a plane like this, and then another one like this, and another like this, and another. Or imagine I just have a whole bunch of parallel sheets of paper, right, one next to each other. So the level surfaces are just parallel planes for 67. Okay, and then 69. F of x, y, z equals y squared plus z squared. So it doesn't say anything about x, but just y squared and z squared. All right, so x can be anything. Okay, since there's y squared and z squared, the left-hand side here cannot be any negative number, right? It's allowed to be 0. So 0 equals y squared plus z squared. That means y and z both have to be 0. X can be anything. So what's any x, 0, 0? That's the x-axis, right? X-axis coming in and out. But y has to be 0. Don't go anywhere left or right. Z has to be 0. Don't go anywhere up or down. So that's the x-axis. For any other positive value of the function, okay, like 1, 1 equals y squared plus z squared. Okay, now you know that that's a circle if I were just looking at the YZ plane, right? Right, now vary x. So take that circle and move it in and out. So you have a cylinder. Same thing if I pick any other positive value, like 4. Okay, that would be a radius of 2. So in the YZ plane, that's y squared plus z squared equals 4. But x can vary. So take that circle and again move it in and out. And again, you have a cylinder. Okay. So that's it. So what do we have? Okay. F of x, y, z cannot be negative. If it's 0, you end up with the x-axis. Any positive quantity, you have a cylinder. Okay. So if you take the plane where x equals 0, the YZ plane, this is a circle. That's a circle. Now you vary x, let x come in and out, so you end up with a cylinder for both of these. And that's about it. Okay. And let me just raise it up again for focusing purposes, a little bit better for you. Hopefully you got all that. Okay, folks, so I'm actually done with 14.1. Start 14.2. So what time is it? So at least I'll introduce this. I'll introduce 14.2, and then we'll see how far I get and whether I want to do any problems before the break or not. Okay, so 14.2, limits and continuity, page 903. Okay, so f of xy equals sine of x squared plus y squared over x squared plus y squared. G of xy equals x squared minus y squared over x squared plus y squared or whatever. Okay, so we're going to take limits now, but the way we write the limits is going to be a little bit different. So first, let me show you this. If I have a function of two variables, okay, remember in Calc 1, limit as x approaches 5 of f of x equals something, right? In 2 dimensions, you have to say limit as xy approaches, let's say 0, 0. Okay, or in this case, limit as xy approaches a, b. That's different. Okay, so in one variable calculus, limit as x approaches 3 of f of x. Here, limit as xy approaches a, b of f of xy equals L. Okay, and yeah, they made a super big table. This time we x comma y approaches 0, 0. We approach the origin. So they made super big table here. They approached the origin from all different directions. Okay, so it looks like they went from -1 to 1 for both x and y. Okay, and if you look real close to the origin, looks like the function values approach 1 in every direction. For this one, they made a similar table. They're saying the limit doesn't exist because depending on which direction you come, this way it looks like it's 1, this way it looks like -1. Okay, limit as xy approaches 0, 0. Now, even this is going to be a little bit different. Okay, so a little bit of theory. So, okay, remember back in Calc 1, limit as x approaches 3 of f of x equals L. And then whatever the function looks like, right? You said, okay, I can come from the left, or I can come from the right, which you can write as limit as x approaches 3 from the left of f of x, right? That's coming from the left side. Or limit x approaches 3 from the right of f of x, correct? Remember that in Calc 1? So, okay, x approaches 3. You can come from the left, you can come from the right. And if you just write this, it's two-sided, correct? Okay. Unfortunately, once you get into function of 2 variables or 3 variables, there's not just 2 possibilities. Okay, how do you approach 3 in Calc 1? You need to come from this side, right? You say 2.9, 2.99, 2.999, 2.9999, right? And this way, 3.1, 3.01, 3.001, 3.001. Come from either the left or the right. Once you get into 2 dimensions or more, you have infinitely many ways that you can approach a point. So it's not enough to exhaust all the possibilities because there are infinitely many possibilities. Okay, now back in Calc 1, right? We said limit as x approaches 3. Okay, I just checked the limit from the left and the limit from the right. That's all there was. And if they were the same, then we said the two-sided limit. Here, xy approaches 0, 0. There are infinitely many ways I can approach the origin. And for emphasis, I'll change color. I can come like that, x-axis, like that, like that, y-axis, but I can come like that. I can come like that. I can squiggle around like that. I can do wheels like that, and right? These are all different ways that I can approach the origin. So I can't just exhaust all the different ways to come to the origin. There's infinitely many, right? Same thing in 3 dimensions. Okay, if I have a point in space right here, or I can come that way or that way or that way, or squiggle around and come here, or loop the loop and eventually come over here, right? So if I want to approach the origin, let's say in 3 space, okay, in 3D, right? How many ways can I approach the origin here? Well, a lot of ways. That way or that way or that way, or squiggle around like that and like that. Okay. So unlike in Calc 1, when we just said on a number line, x approaches 3, only 2 ways, left and right. Not so here. How many ways can I approach a point? Let's say the origin. That's the easiest point. I could approach 3, 5 or -2, 7 or whatever. There's infinitely many ways. There's also infinitely many ways I can approach the origin in 3 space. All right. So now we're considering limits in this situation. So we're going to try to, and don't worry about this formal definition. I'm not asking you any questions about it, but it's very similar to what you may have had in Calc 1, if your Calc 1 teacher went over epsilon and delta. Okay. If you say, I don't know what you're talking about for epsilon and delta, then don't worry about it. But here's a very formal definition of saying closeness, right? When x comma y is close to a, b, then f of x is close to L. Right, so this is an equivalent definition, but I don't even give you any homework problems involving that, so don't worry about it. If you know what I'm talking about, great. If you've never seen this before, don't worry about it. Okay, now it's pretty easy to show that a limit does not exist. Example 1. Limit as xy approaches 0, 0, x squared minus y squared over x squared plus y squared does not exist. Now, remember in Calc 1, it was real easy if you could plug in and you weren't dividing by 0, right? So if you weren't dividing by 0, like this is x squared plus y squared plus 1, then it's easy, just plug it in, that's the limit. It's only trouble if you divide by 0, okay? Which is the case here, right? There's no way you can do this by exhausting the possibilities, but it is easy to disprove that the limit exists, okay? By just showing 2 different paths, giving me 2 different numbers, okay? So if you look over here in figure 4, page 905, they show you 2 paths. See the path in red along the x-axis? This is the function is 1. Then look at the path along the y-axis, the function is -1. Okay, so that means the limit does not exist. Okay, we're used to saying 2-sided limit. There's no 2-sided limit, there's an infinite-sided limit. Okay, but we can establish that the limit does not exist. We'll be doing a lot of problems like that. Okay, so if I come along the x-axis, that means y equals 0. So I plug in a 0 here and a 0 here, you get x squared over x squared, which is 1, right? Then if I come along the y-axis means x equals 0. Put a 0 there and a 0 there, you get negative y squared over y squared, which is -1. Okay, so that proves the limit does not exist. I found 2 different paths with 2 different limits, right? So one approaches 1, the other approaches -1. So that's enough to say that the limit does not exist. Okay. However, suppose both of those limits came out to be 1. Okay. So figure 4, the red came out to be 1, the blue came out to be 1 also. Does that prove that the limit is 1? No, it does not, unfortunately, right? For how do I know, right? If this came out to be 1, this came out to 1, maybe if I come some other way or some other line or go along a parabola, maybe that's a different limit. So you cannot prove a limit by exhausting all possibilities. But it's usually easier for these homework problems to show that a limit doesn't exist, but just establishing 2 paths. Okay, so in short, you cannot prove a limit by establishing any number of, I mean, I can find a million paths that all approach 1. That still doesn't, how do you know the 1,000,001st path doesn't come out something different, right? But as soon as I find 2 different paths to give different limits, I can then say the limit does not exist. Okay, yeah, I want to show you figure 3 here, where they're trying to show you there's infinitely many ways where x comma y can approach a comma b, right? So you can go that way or that way or that way or squiggle around over here. Those are all legitimate paths toward the point a comma b, right? So as you can tell, it's a much more rich variety than we had in Calc 1. I mean, now that you get into the multi-dimension, the Calc 1, you might say, oh, this is too ordinary, this is too boring, right? Okay, you can only come left or right, you know, either from the 2.9, 2.99 side or 3.1, 3.01, and that's all you can do. But once you get into higher dimensions, well, you have a lot of ways that you can approach a comma b, right? So that's what's happening here. Now, I'll just show you what's happening. At what time is it? A little bit before 7. Still okay. Okay, so 14.2. Five to 21 odd, 29 to 37 odd. Find the limit if it exists. Okay, number 5 is, it's almost as easy as the Calc 1 example. Just plug it in, right? Remember in Calc 1, the first limits you probably did were trivial, right? And you said, that's no big deal, just plug it in, right? 16 minus 5 equals 11. Too easy. Okay. And then you got more sophisticated. Okay, there weren't too many problems like that because otherwise it's just like algebra 1. Then you did a whole bunch of problems where the denominator came out to be 0, right? Which led to the definition of the derivative, limit h approaches 0, f of x plus h minus f of x all over h, right? Okay. So harder was something like this, slightly harder. Okay, you say, oh, you can't plug in, dividing by 0. Okay, or maybe you can do some algebra trick, right? So in this one, limit as x approaches 0, x parentheses 3 plus x divided by x, and then you can cancel, and then you plug in. Remember that? Okay. So same kind of thing for this. Number 5, dare I say, I don't have to talk about it, just plug it in. Right, number 5, x comma y approaches 3 comma 2, just plug it in. Again, the point is real close to 3, 2. So maybe 2.999 comma 1.999, right? But anyway, just plug it in. 7, just plug it in, right? So those are too trivial, I dare to say. It gets more interesting with something like number 9, right? Because number 9, you're dividing by 0. So that's where you have to do something different. Okay, only for very few problems can we actually prove the limit. Okay, and I'll show you some examples of those. Okay, let's see, what time is it? It's not even 7 yet. Okay, so maybe I'll get started with a few problems and we'll break and then go on from there. Okay, so 14.2, page 910. Too easy, right? Limit as xy approaches 3, 2, x squared y cubed minus 4y squared. You're not dividing by 0. You're not taking the square root of a negative, anything. Just plug it in. 3 squared, 2 cubed minus 4 times 2 squared. I won't bore you with the details. 56. Again, officially, what this is saying is not when you plug in 3 for x and 2 for y, you get 56. Okay, we're really saying if you plug in a point that's really, really close to 3, 2. And by the way, x and y, you're allowed for x to be 3 as long as y isn't 2. So 3 comma 2.001 is allowed. Okay, or 2.9 comma 2, that's allowed, just so long as 3 and 2 are both not there. So if I plug in a number which is close to x equals 3, y equals 2, I get 56. Okay, so now for the meatier problems, what are the harder problems like? Okay, so number 9, limit as xy approaches 0, 0 of x to the fourth minus 4y squared divided by x squared plus 2y squared. Okay, you know you can't plug in. Okay, so here's a case where we hope we get does not exist. So let's just try to establish two paths where I get different limits. Okay, the easiest paths to pick are along x equals 0, which is the y-axis, and along y equals 0, which is the x-axis. Okay, so you would start off with that as your first guess, right? That's just like this figure 4, right? So see the red? That's the x-axis, which means y equals 0. I plug in y equals 0. And in the blue y-axis, I plug in x equals 0. Okay, so here's what you do. Along x equals 0, that's the same as the y-axis. First, do you agree that if you're along the y-axis, you do approach the origin, right? If you come real close. So I just plug in 0 for x. Put a 0 there and a 0 there. You get negative 4y squared over 2y squared, which is negative 2. Limit as xy approaches 0, 0. I know even this gets kind of clumsy to write. Okay, you're used to writing limit x approaches 5. Now you have to write an ordered pair, x, y, comma, ordered pair, or maybe even an ordered triple later on. Right, you might have to write an ordered triple, x, y, z approaches 0, 0, 0. Okay, so if I come along the y-axis, x equals 0, the limit is negative 2. Then I try along y equals 0. So y equals 0, another way of saying y equals 0 is the x-axis. So plug in 0 right there and right there. I get limit as xy approaches 0, 0 of x to the fourth over x squared, which is the same as x squared. Okay, so then when x and y approach 0, the limit is 0. Okay, so I found two paths, okay, that give different limits. If I come along the y-axis, x equals 0, the limit is negative 2. If I come along the x-axis, which means y equals 0, the limit is 0. Therefore, the limit does not exist. Okay, so that's the usual thing that you'll be aiming for most of these problems. And frankly, most of these problems, the answer is D and E. If the limit does exist, we have to do some other algebra trick for that, and I'll show you that probably after the break. But again, watch out. If this came out to be 0, and this also came out to be 0, does that prove that the limit is 0? No, it does not. It only shows it's true for two different paths, but you have infinitely many other paths, okay? And there's no way you can, show all the infinitely other paths in general, unless there's something very specific about the problem that lets us do that. Okay, but we'll go ahead and take a break right now, and we'll continue this after the break. Okay, so let me stop the share, 6:55-ish. Okay, how about 7:10? We'll start up again at 7:10, and we'll break, and I'll break and disappear also. Okay, so 7:10, I'll put it in the chat. Okay, so 7:10, and I'll put it in the chat also. Okay, folks, it's 10 after, so we'll go ahead and start up again. We're probably going to finish very early. Okay, I'll knock off these problems, and I mean it's only 7:10. Class ends at 8:25. Okay, so I can probably tell you a little bit about what 14.3 is about. I wasn't going to do any problems in 14.3. I think that's too much. Okay, but I'll just tell you a little bit what it's about, and then I'll just let you ask questions. And if you don't have any questions, we can just call it a day. Okay. And then, so again, next time I was aiming for 14.3 minimal. And I think that's going to be quite easy to do, especially if I sneak a little bit in today, just tell you what it's about. Okay, and then again, second half, you can ask me any questions pertaining to the tests, which is this stuff, 13.1 to 13.4. And a reminder, even on the test day, next Tuesday, I will lecture a while, quote unquote, just like last time, not that long, that you ask questions, then we break it, and the test will be the second half of class on Tuesday of next week. Okay, I'm leaning toward, like it says in the schedule, giving you the entire class period of 2 hours plus for exams 3 and 4 and 5, just because some of those problems take really, really long to do. Okay, I'm not saying hard. I don't think they're necessarily hard, but they're just long, so to speak. Okay. And let's see. Are we likely to push up the next test since we are so far ahead of schedule? I'm not sure we are really that far ahead of schedule. Because, you know, if I could move everything up one day, that's already where we're at. And I'm always weary of possibly losing a day because my internet goes down, which is what happened last semester, or I got sick or something like that. So we'll see how it goes. Okay, so it's too early for me to tell right now, I guess. But yes, the safest thing to say is for now, let's just plan on the third test being as it stands. And if it changes, then I'll let you know. Okay. All right, so more of these limits. Again, if you could just plug in, then do so. Like number 5, and I think number 7 was also, it's really no big deal, just plug it in, right? So there's trouble when you divide by 0, as the case. Remember in Calc 1, you had a lot of those also. Okay, so here's number 11, where something a little bit unusual happens. Limit as xy approaches 0, 0. Y squared sine squared x over x to the 4th plus y to the 4th. Do that like that. Okay, you can't just plug in. By the way, if this one said 0, 1, you don't have to do anything, just plug it in. Every time you see x, put a 0, and every time you see y, put a 1. You're not dividing by 0, right? There's no issue. So it's only in this case. All right, so along x equals 0, that's the y-axis, okay? Yeah, if you come along the y-axis, you are approaching origin. So put a 0 right there. Sine of 0 is 0, right? So the numerator becomes 0. Put a 0 there. And you have 0 over y to the 4th. And as long as y is not 0, and it isn't, because x, y approaches 0, 0. If you're saying x is 0, that means y is non-0. Then 0 divided by y to the 4th is 0. Okay, now you notice in this particular instance, and yeah, sometimes you say, how do you know what to plug in ahead of time? You don't. Just try different things. I mean, this in itself is a rich variety. I mean, you could spend hours and hours of solving problems that are like this. Okay, but if I come along y equals 0, it's pretty easy to see that the limit is also 0. Okay, put y equals 0. Put a 0 there. The numerator is 0, right? Put a 0 there. That's 0. So you have 0 over x to the 4th. And what's 0 over x to the 4th? 0. Okay, so I don't want to also come along y equals 0. Yes, I do get a limit, and that's 0, but that does not prove the limit is 0. That does not disprove the limit is 0. Okay, so what do I do next? Okay, the hint for this one is I see a sign there, right? Okay, question, does the sine function go through the origin? That's like saying it's a sine of 0, 0. Yes, it is. So because there's a sign here, if I put a sign here, then I would have something involving sine to the 4th. Each of these has something to the 4th power, right? So that would be the way to go. Let's try that. That's not a guarantee that it works, although I think it works in this case. Okay, so I'll come along y equals sine x. So I'm coming to the origin along the sine curve. So right there, put sine x. Right there, put sine x. So I have sine squared times another sine squared, sine to the fourth, over x to the fourth plus sine to the fourth of x. And then divide top and bottom by sine to the fourth. Okay, a trick from Calc 1. X, y approaches 0, 0. So sine to the fourth. Okay, one more time. Put sine squared x right there. You have sine squared x times sine squared x, sine to the fourth x. And put there sine to the fourth of x. Okay. Now divide top and bottom by sine to the fourth of x. Sine to the fourth x over sine to the fourth x divided by x to the fourth plus sine to the fourth x over sine to the fourth of x. Okay. So in other words, divide that by sine to the fourth, divide that by sine to the fourth. This is 1. This is 1. And this is x over sine x to the fourth power. That's the key. Okay. So now x, y approaches 0, 0. There's no y here. Do you remember this limit as x approaches 0? X over sine x from Calc 1? That's 1. Okay. Or you could also do L'Hopital's rule. Remember L'Hopital's rule? You get 0 over 0. Take the derivative of the top and the derivative of the bottom. Right? What's the derivative of x? 1. What's the derivative of sine x? Cosine x. Plug in 0, then you have 1 over 1, which is 1. Okay. So we now have 1 divided by, yeah, the limit of a product is a product of the limits. Limit of a quotient is a quotient of the limits. So I'm allowed to sneak in the limit down here. 1 over limit xy approaches 0, 0 of x over sine to the x to the fourth power plus 1. Okay. And this limit was 1. You might recall that from Calc 1. That's 1. 1 to the fourth is 1. So I have 1 over 1 plus 1, or 1/2. Okay, so there it is. I have what I want. Okay, so I have one path along x equals 0 where the limit is 0. I took another path in my head along y equals 0. You also got 0. That does not prove the limit is 0. That does not disprove the limit is 0. Right? It's not like in Calc 1. Right? Calc 1, you say, oh, I can prove the limit, the two-sided limit. I come either from the left or the right. That's all there is. And if the limit from the left and the limit of the right are the same, then I'm done. Not so here, because once you go into 2 dimensions or 3 dimensions, there are infinitely many ways you can approach the origin. Right? So the trick for this one particular problem was the third path to try was along y equals sine x. Along y equals sine x, the limit was 1/2. Therefore, the limit does not exist. Okay. Okay, 13 is definitely trickier, a lot harder. Limit as xy approaches 0, 0 of xy over the square root of x squared plus y squared. Okay, now I claim this limit actually exists. Okay, and I'll show you how to do this one. Okay, there's no set way to do this per se. I mean, you could say plug in x equals 0. I got 0 over y, that's 0. You can plug y equals 0. Then you get 0 over x, that also gives you 0. Okay. But again, you can't prove it just by coming along several different paths. Even if I demonstrate 1,000,000 paths that gives a limit of 0, that doesn't prove it. Instead, here's a trick that you would do for this one. Okay. Underneath the radical, divide by x squared plus y squared. Okay. Now, what is the equivalent over here? Okay. The square root of x squared plus y squared, very technically, it's not xy. It's the absolute value of xy. Okay. When I go like this, when I put x squared plus y squared, x squared plus y squared, the square root of x squared plus y squared, very, very technically, is not xy. It's the absolute value of xy. Because x can be negative and y could be negative. So I have this. Okay, now the top is plus or minus 1, right? Okay, you can do some finagling around, but I've got the bottom to be this 1 over y squared plus 1 over x squared. Okay, you can split this up into 2, right? X squared divided by that is 1 over y squared. And then y squared over that is 1 over x squared. Okay, so the numerator is plus or minus 1, right? Xy divided by absolute value of xy. It's either going to be 1 or negative 1. But look at the bottom. X, y approaches 0, 0. Both of these are very, very small, right? So the numerator is plus or minus 1. The denominator is a very small number. That's going to make this whole thing big. Okay, so one more time, plug in 0.0001 and negative 0.001. Okay, that makes this thing huge. So the numerator is either plus or minus 1 divided by a huge number. That makes the limit 0. Okay, a little bit tricky for that one. So that's how this particular one works. To be honest with you, yes, you might say, I never would have guessed that. You're probably right, unless you're used to seeing these kind of problems. Okay. And we're barely scratching the surface. You can come up with all kinds of really weird functions where you're just guessing around, right? How can I show the limit exists or doesn't exist? But that's how you do these problems. And whatever I give you on the next exam, after this, would only be something of the nature that I've shown you. That would be only fair. Okay. Okay. 15. Limit as xy approaches 0, 0. Xy squared cosine y over x squared plus y to the 4th. Okay. So again, the object is to come along 2 paths and see if there's 2 paths that give you different values. Okay. The easiest to plug in are x equals 0, y equals 0. So plug in x equals 0. That makes the numerator 0. The bottom is y to the 4th, right? Put a 0 there. That's all 0. So 0 over y to the 4th, that's 0. Okay, now, again, I notice if I plug in y equals 0, I also get 0. Put a 0 right there, the numerator 0. Put a 0 there, you have 0 over x squared, that's 0. So that's not going to help really. Okay. Instead, the key for this one is this. Okay, see x y squared, x squared y to the 4th. If I want to get it down to a single variable and the same exponent, I'm going to try for x being y to the 2nd power. Okay, so that's why I choose x equals y squared. Say, come again. Okay, if I put a y squared there, I notice that's going to be y to the 4th. If I put y squared there, I have y squared squared, which is also y to the 4th, and I can combine it with this y to the 4th. Okay, so that's what leads me to choose along the path x equals y squared. Okay, what does x equals y squared look like? It looks like that. And does that come into the origin? Yes, it does, right? So if I come close to the origin along the path of this parabola, x equals y squared, you see. Okay, so that means put y squared right there, y squared cosine y. Put y squared right there. So it's y squared squared, y to the 4th plus y to the 4th. So that gives me y to the 4th over 2y to the 4th. So limit as xy approaches 0, 0, y to the 4th cosine y over 2y to the 4th. The y to the 4th cancel out. Limit as xy approaches 0, 0 of cosine y over 2. Now I can directly substitute. Plug in x is 0. Don't have to worry about that. Y is 0. Cosine of 0 is 1. 1/2. Therefore, the limit doesn't exist. Okay, it's very, very tricky. Okay, so if I come along x equals 0, if I come along the y-axis, anyway here, the limit is 0. If I come along the x-axis, the limit is also 0. But if I come along a different path, in this particular case, x equals y squared, if I come along here, the limit comes out to be 1/2. So again, since I've established two different paths with two different limits, we can overall say the limit does not exist. Okay. Yeah, pretty strange how these problems work, no doubt about it. Okay, the next one I was going to show you is 17. This one, you might recall a trick from Calc 1. 17. Limit as x, y approaches 0, 0. X squared plus y squared over radical x squared plus y squared plus 1 minus 1. Okay. Direct substitution gives you 0, 0. The trick is to multiply by the conjugate of the denominator. Remember you doing something like that before? So you can't plug in right away. If you plug in 0, 0, 1 minus 1 is 0. Okay. So multiply by radical x squared plus y squared plus 1 plus 1, top and bottom. Remember doing stuff like that in Calc 1, right? So that way the numerator is x squared plus y squared times radical x squared plus y squared plus 1 plus 1. Don't multiply that out. The bottom looks like a minus b, a plus b, right? A minus b, a plus b is a squared minus b squared. So what is the radical squared? X squared plus y squared plus 1. Minus b squared, 1 squared is 1. Well, notice the 1's cancel out. So you just have x squared plus y squared, which very conveniently cancels out that x squared plus y squared, right? Okay, remember doing stuff like that in Calc 1, right? You multiply by the conjugate and then you get stuff to cancel out. So all that's left is limit as xy approaches 0, 0 of radical x squared plus y squared plus 1 plus 1. And now you can just plug in. So put a 0 there, radical 1 plus 1. So my final answer is 2. Okay. So that's the trick for 17. All right, and then just a brief introduction to give us some three-dimensional points at the very end, like 19 and 21. Okay, so 19, x, y, z approaches pi 0, 1/3, e to the y squared tan xz. Just plug it in. Okay, so 19, there's no trouble, just plug it in. That's your answer. Fair enough? So they're a three-dimensional point. Okay, so the point was 0 or pi 0, 1/3. So it's a point in space, right? So here we are. And when we say the limit as x, y, z approaches whatever it was, pi 0, 1/3. So you can come this way or this way or this way or squiggle around. Okay, you can be real creative and do all kinds of things until you land at that point. Okay, much, much different than in Calc 1. You approach only from the left and the right, correct? Say limit x approaches 5, where you come either from the left or from the right, but that's all you can do. Okay. So again, so 19, just plug it in, no big deal. Okay, so the only thing that's semi-interesting is 21. So limit as x, y, z approaches the origin of xy plus yz squared plus xz squared over x squared plus y squared plus z to the 4th. Okay, so what's the trick for that one? Okay, so the easiest thing to do here is to let two of the variables be 0. So for instance, let x equal 0 and y equal 0. If x equals 0 and y equals 0, that's gone, that's gone, that's gone, that's gone, that's gone. I have 0 plus 0 plus 0 over 0 plus 0 divided by z to the fourth. Essentially, you have 0 divided by z to the fourth, and z is not allowed to be 0 if x and y are already 0, and that's just going to be 0. Okay, how do I pick another path? Okay, and again, you kind of have to be creative with these, but I notice over here there's a z to the fourth, right? So it'd be nice if I can force everything else to have a z to the fourth, right? So I notice x times y, y z squared, x z. So if each of these was a z squared, if that's a z squared, that's a z squared, that'd be z to the fourth, that's a z to the fourth, that would be z to the fourth, it'd be z squared squared, that would be z to the fourth, and that would be a z squared times a z squared, which is also z to the fourth. So I can force all of these to have a fourth power in it if I let x equal z squared and let y equal z squared. Okay, so along x equals z squared, y equals z squared. Okay, so I'm coming along the path x equals z squared, y equals z squared. Does that approach the origin? Yes, it does. Right, 0, 0, 0 works for all of these. Okay, so the strange path that I'm picking is along x equals z squared, y equals z squared. That does go to the origin. Again, the reason why I picked that is that forces 1, 2, 3, 4, 5, 6 expressions to all have a z to the fourth. Okay, so I saw there's a z to the fourth. So if I have x is z squared, y is z squared, that's going to be z squared, z to the fourth. That's going to be z squared, z to the fourth. That's going to be z to the fourth. That's going to be z to the fourth. That's going to be z to the fourth. Okay, so that's the trick for this particular one. So the path I'm picking is along x equals z squared, y equals z squared. Okay? So put a z squared. Every time you see x or y, put z squared, basically. Okay, so that's z squared, z to the fourth. That's going to be z squared, z to the fourth. That's going to be z squared, z to the fourth. That's going to be z squared, z to the fourth. That's z squared, z to the fourth, and that already was z to the fourth. So basically you get 1. Right, so I got 2 different paths with different limits, so the limit does not exist. Okay, so that was definitely a lot tougher problem also. Okay, if you pick going along y equals 0, you get 0. Or if you pick, let's say, x equals 0 and z equals 0, okay, you would also get 0. So that's the reason why I picked another path like this. Okay. So now the problem is at the end. Talk about continuity. Okay. Determine, let's see. So I'm doing 29 through 37 now. I'm done with 5 to 21, basically. So 29 to 37. Determine the set of points for which the function is continuous. Okay, just like in Calc 1, if you have multivariable situations, okay, all functions, unless they're piecewise defined, they're continuous everywhere on its domain. So you have exponential and logs and square roots, trig, inverse trig, they're always continuous wherever they're defined. So we're basically just asking, where's the function defined? It's almost like asking, where's the function defined, as it were. So determine the set of points of which the function is continuous. Okay. All right, 29. F of xy is xy over 1 plus e to the x minus y. Okay, polynomials are continuous, x times y. Exponential is continuous. 1 plus continuous is continuous. The sum of continuous functions is continuous. The quotient of continuous functions is continuous. So I really just need to say, when is the denominator 0? So I set 1 plus e to the x minus y equal to 0. Subtract 1. That means e to the x minus y is equal to -1. But we recall that can never happen. That can't happen. E to anything, e raised to any exponent is positive. So that can't happen, which means there's no trouble spot. So the domain is quote unquote everything. And you have to be careful now because your gut reaction from Calc 1 is say everything works, all real numbers. But no, we're in R2 now. Right? If I say f of xy, the biggest set is R2, which is the xy plane. If you're in R3, f of xyz, the biggest set is R3, the set of all points in space. Okay, anywhere you want in x, y, and z. Okay, so here we are saying quote unquote everything works, but in this particular case, we say R2. Okay, so remember in Calc 1, right? When you said everything works, you just said all real numbers, because the largest set you start off with is a set of real numbers. But here, the largest set we start off with is R2, xy plane, or it might be R3. Okay, 33. G of xy equals square root of x plus radical 1 minus x squared minus y squared. Okay, so the largest set is R2. Well, you can tell from here that x has to be greater than or equal to 0. Little bit of algebra here, x squared plus y squared has to be less than or equal to 1. I trust you can do that algebra. You're saying 1 minus x squared minus y squared is greater than or equal to 0. So just add x squared and y squared to both sides. You have this. Okay, that is unit circle and the interior, but I only want x is greater than or equal to 0. So here's my domain, okay, from the graph. So that's it. So if we're talking about a function in 3 space, right, the only z values that you have are coming from here. So you don't have all of the xy plane. It's a limited domain. Only along this semicircular region are there heights. So maybe right here, the height is here. And over here, there's a different height. And over here, there's a different height. But over here, there's no z value. Over here, there's no z value. Over here, there's no z value. The only points where there's function values above it are this semicircular region. And again, I say above, it could go down, but in this particular case, you're not going to go down because that's non-negative and that's non-negative, right? So that takes care of that. Okay, 35, a function in 3 variables. So for 35, you start off with R3. The biggest possible set is all the set of all points in 3-dimensional space. F of x, y, z is arcsine x squared plus y squared plus z squared. Okay, so you might recall from trig that you can only take the arcsine of stuff between -1 and 1. Okay, you can take the arcsine of 1, that's pi over 2, 90 degrees. You can take the arcsine of -1, negative pi over 2, negative 90 degrees. Okay, so that means x squared plus y squared plus z squared, everything behind my finger, has to be between -1 and 1. Okay, well, you can look at this. That's already going to be greater than or equal to 0, right? X squared plus y squared plus z squared. So you can pretty much just get by with only this part. Okay, this is demanded by the arcsine, but x squared plus y squared plus z squared already can't be negative. So you just look at this. So this is the unit sphere and its interior. Okay, so I just drew myself a unit sphere and the interior. Okay, so that's a set of all points for which the function is continuous, which in this case is almost like saying what's a domain. So there are function values on the unit sphere. The unit sphere, center of the origin, radius 1. That's a 3-dimensional analogy of the unit circle, right? What was the unit circle? Center of the origin, radius 1. What's the unit sphere? Center of the origin, radius 1. Difference is that you're in 3 space now. And of course, for the origin, instead of saying 0, 0, the point is 0, 0, 0. Okay, so that's supposed to represent the unit sphere radius of 1. Okay, 37 is the last one. And then I'm actually done with the section, folks. And what time is it? Only 7:40-ish. Okay, so I'll be done. So maybe 14.3, I'll just give you a brief introduction to what it's all about, and then let you ask any questions. And if you don't have any questions, you can still ask questions next time if you want to prepare for the test. And that would actually be my preference, but that's okay. So I'll just tell you what 14.3 is about, and that's about it. Okay, 37. They write it kind of funny. It's a piecewise defined function. Let's see, where'd it go? Here we are. F of xy equals x squared y cubed over 2x squared plus y squared if xy is not 0, 0. And it's equal to 1 if xy is 0, 0. So this function is defined for all of R2. Every point in the xy plane will have a height. Right? Because if you look at the top rule, that's defined for any xy except the origin, right? The only time the bottom is going to be 0 is when I plug in 0, 0. But like a piecewise defined function, if you are at the origin, the height is 1. Okay, so for sure, this function is going to be continuous everywhere except maybe the origin. Correct? This is a rational function, polynomial divided by polynomial, which is always continuous everywhere it's defined. Okay, so bare minimum, I have all of R2 minus the origin. So is it continuous also at the origin? Okay, so let's see. All right, so the easiest way to do this one is just try to find a limit which is not 1 as I approach the origin. Since the function value is 1 at the origin, if I can find a limit which is not equal to 1, that automatically makes the function not continuous at the origin, right? That's actually very easy to do. Easiest to do is come along either x equals 0 or y equals 0. Okay, so if I come along x equals 0, put a 0 there, that makes numerator 0, right? Put a 0 there. So limit as xy approaches 0, 0 of x squared y cubed over 2x squared plus y squared. Raise it up there. Okay, plug in 0 for x. 0 is on top. 0 plus y squared. And so I get 0. That pretty much does it. Because I now know that the limit as xy approaches 0, 0 of f of xy is not equal to f of 0, 0. Okay, f of 0, 0 is 1, which means that the function is going to be continuous. Every path that I take coming to the origin has to have a limit of 1. But I found one path where the limit is 0. So limit xy approaches 0, 0 of f of xy, which I actually haven't even established. Okay, but I know for sure it isn't 1. Okay, because I got one path where it's 0. Okay, so where's the function continuous? Everywhere except the origin, and here's how we write it. R2, which is the xy plane, minus a set consisting of the origin, 0, 0. So the braces indicates a set of numbers. I mean, you don't have to graph it, but the idea behind the graph is you would have an open circle here, and you literally shade everything else. Is that you have the entire xy plane, just punch a hole at the origin and throw it out. Okay. And you did stuff like that in one dimension, right? In one dimension, it's like say, how do you say all real numbers except for 0, right? So the graph would be you shade all of this. Is that so you could say all real numbers minus the set consisting of 0. So this is the set of all points in the xy plane, R2, minus the origin, the set consisting of the origin, 0, 0. Okay. All right, folks, I've accomplished everything I wanted to accomplish, which is 14.1 and 14.2. It's only about 7:45-ish. Okay, so I can mark this off. Okay, so I was going to do 14.3 next time. I'll give you an introduction to that, which will not take that long. And then if you have no questions, we can just end. But if you have any questions, you can bring that up too. So if you want to put stuff in the chat now, you may. But I'll just tell you what 14.3 is about, which I'll get to next time. So again, the exam is next Tuesday. So quick introduction, which will save me some time next time. 14.3 is on something called partial derivatives, page 911. Okay, and when we say partial derivatives, it's not partial like that's a half a derivative or a third of a derivative. No, they're full derivatives, but they have more than one part to it. Okay. So we have a function of more than one variable. Okay. Now you can look at all this and you can look at all this, but I don't think you really need to. Okay. Partial derivative. Okay. Now we have a function of two variables. Let's say f of x, y. Okay. And they don't give me an example right here, but let me just show you something from the homework, I suppose. Oh, look at 15, 17, 19. Function of two variables, right? I want to talk about the derivative. Well, we kind of have a problem because if I only had x, like for 15, I know what to do. If I only had y, I know what to do. I have x and y. So how do I take a derivative? Well, it depends. I could take a derivative with respect to x. I could also take a derivative with respect to y. Okay. And we'll learn there's other ways you can take a derivative also. Okay. Now, here are formal definitions of partial derivatives. Okay. You don't really have to write these down because there are no homework problems involving it. Okay. But partial derivative of f with respect to x, partial derivative of f with respect to y. Okay, so you can take the derivative with respect to x, you can take a derivative with respect to y. So two different parts of a derivative. That's why it's called a partial derivative. You can take the derivative with respect to x, or you can take the derivative with respect to y. And when you have a function of three variables, f of x, y, z, you can take the derivative with respect to x, y, or z. Okay, so you can't just say take the derivative. Well, am I differentiating with respect to x, or am I differentiating with respect to y, or differentiating with respect to z? So there's more than one part to it. Okay? So it's a full derivative. They're full derivatives. You're taking the derivative with respect to x, or take the derivative with respect to y, or take the derivative with respect to z. The concept is kind of like this. Okay, if you have some three-dimensional shape, the derivative with respect to x, you're only going in the x direction. And strictly speaking, when I say derivative with respect to x, that's a positive x direction, so coming directly out at you. If you take the derivative with respect to y, you're only going in the y direction. Okay, and when we say derivative with respect to y, it's only in the positive y direction. Okay? And if you have a function of three variables, derivative with respect to z, you're going specifically in this direction. And you say, what about going some other direction? We'll have that too. Okay, so once you get into multivariable, you can have all kinds of this. So how about the rate of change of the function? If I want to go that way or that way or that way or that way, we can have all of those too. Which actually now makes Calc 1 boring, so to speak. All you have was dy dx, right? Rate of change of y with respect to x. But now that you know that there's a whole bunch of other things, so what Calc 1, rate of change of y with respect to x, is that all? So to speak, well, we got rate of change with respect to x, with respect to y, with respect to z, or maybe go that way or that way or that way or that way. Okay, we can have the rate of change going in any direction that we want. Okay. All right. On page 914, I'll show it to you, but you don't really need to know it. There are no homework problems involved. Okay. The partial derivative of f with respect to y. Okay. If you reason it out, it's actually very logical, but don't really look at it if you don't want to. And here's the formal definition of the the rate of change of the function with respect to x. Whoops. Where'd it go? Equation 2. It's there. It's correct. It sort of looks like a formal definition of a derivative back in Calc 1. Okay. What I do want you to know is this, and then I'm pretty much done. Page 19. The notation for partial derivative. There's a whole bunch of them. The most frequent ones are these. Okay, z is a function of x and y. Okay, partial of f for function with respect to x. Okay, you can use this backward 6. See that backwards 6 kind of line? Okay. That's supposed to sort of represent a d, like dy dx, right? Or df dx, or partial of z with respect to x. But it doesn't look like a real d. It's only like a part d, hence partial, haha, bad joke, partly a d. Okay, so one notation for partial derivative is a backward 6. So partial of f with respect to x. Also, f subscript x, fx. That's the one I like the most. So I'll be using that most frequently. So again, just like the I, J, K stuff, I only write this occasionally, quote unquote. The backward 6 partial of f with respect to x. I prefer fx. Likewise, partial derivative with respect to y, fy, or backward 6f with respect to y. It looks like partial of f divided by y, but that's a partial of f with respect to y. Okay, so again, that backwards f. You could also write that. That's too much writing in my opinion. And f is the same as z right now. Remember, z is the height. So now we're calling that the height, just like y used to be the height, right? Y used to be the height. So partial of f with respect to x, partial of z with respect to x, partial of z with respect to y. Okay. And those ones at the end, I'm almost never going to write f1 or f2. I'm never going to write that. d1f, d2f. I'm never going to write that. Okay. The ones you want to focus on mostly are, let's see, these and these. Partial of f with respect to x or fx. Partial of f with respect to y, fy. Okay, how do you take the derivatives? Here are the rules. You can put this on your next cheat sheet if you want, but it's really not that bad. I think you can all get it. Okay, this is not for this Tuesday's test. It's the test after that. Okay. Rules for finding partial derivatives of z equals f of x, y. To find a partial of f with respect to x, treat y as a constant and then differentiate with respect to x. And likewise, number 2, to find fy, regard x as a constant and differentiate f of x, y with respect to y. Okay. So when you see the function of x and y, when you're taking the derivative with respect to one variable, treat the other variable as a constant. And that actually makes sense. Okay. If you look at the, for instance, xy plane, okay, if I take the derivative with respect to x only in the x direction, well, y is constant, right? And if I go only in the y direction, strictly up and down, x is a constant. You're not changing x. So you simply treat the other letter or letters as constant. That's all you have to do. So I'm almost done in a couple of minutes. So to take a derivative, maybe I can just talk about one of them. Find the first partial derivatives of the function. Okay, so in Calc 1, we just said the derivative, right? Now I have a function of two variables. You can't just say the derivative because there's two parts to it. That's why we say partial derivatives. You can take the derivative with respect to x and derivative with respect to y. Okay, so for 15, let's say, to take the derivative with respect to x, pretend y is a constant. That is like a constant. So differentiate with respect to x. So what's the derivative of x to the fourth? 4x cubed. what's the derivative of 5xy cubed? Y cubed is a constant. That means the coefficient of the second expression is 5y cubed. The constant, quote unquote, is 5y cubed times x. Therefore, the derivative is 5y cubed. It's just like saying the derivative of kx. Now, if I were to ask for the derivative with respect to y for 15, this whole thing is constant, so that would be 0, right? Look at 15, x to the fourth. What's the derivative with respect to y? Well, x to the fourth is treated as constant, so that's 0. Then how about 5xy cubed? Pretend 5x is a constant. So you're basically differentiating y cubed. So you go 3 times 5x, which is 15x, 15xy squared. That's how you do it. Okay, and that is all I was going to do. That's my introduction to 14.3, which will just save me a little bit of time next time for that. Okay, so I've actually done even more than I had wanted. So 14.1, 14.2, I snuck in introduction to 14.3. So next time, 14.3 was my goal. And then after the break, you can ask me any questions about chapter 13, but if not, I might very well just go ahead and go on after that. Okay. All right, I'm done, folks. So let me check the chat. I don't think there was anything in the chat. Let's see, not yet. Okay, so if you have any questions, you can put in the chat or unmute yourselves. Otherwise, we can call it a night. And yeah, maybe next time, if you have any questions for chapter 13, you can bring it up next time in preparation for the test a week from today also. Okay, and let me swing back to the chat. I think we're good. Okay, so anybody else?
I did have something. For 14.1, number 69.
Okay, unfortunately, I think someone's trying to say something, but I can't quite hear, so maybe that's a problem with having this. I'll try to turn up the volume. I'm sorry, or maybe if someone had a question, can you put it in the chat, please? Maybe there's something about using this thing where I can't hear you guys that much. But anyway, so anybody else with a question, please? Or maybe I was just hearing some feedback somewhere else. All right, I don't see anything or hear anything, so let's call it a night. Okay, so let's quit and we'll see you next time on Thursday. All right, see you guys next time. Okay, so bye everybody. Oh, Rashan, sorry. Ask next time, Rashan. Sorry.
Okay.
I already
All right.
closed it out. So yeah, ask me next time, Rashan. Thanks.
Okay.
Okay, thank you. Or else you can send me an email.